Hello everyone. Uh, yeah. I hope I'm audible and my screen is properly visible to all. In case, by any chance, you feel I'm going too fast or if I'm going too slow, please let me know. I'll accordingly alter my pace. And once again, thank you so much for sharing the forum and giving this opportunity to talk about the stuff. The intention here is obviously to go through this book and understand things and share what I have understood. For with certainty, I can say I've not understood things completely. There are a few gaps which I definitely will definitely throw it in the open forum so that we can have a quick discussion. And I see some really good participants available over here, which I'm sure should be able to throw some light on those queries or doubts. So that's the intention. So with that note, I think so we will get started. So this chapter basically talks about storage and retrieval. And the key point that the chapter starts with is how we can store the data that we are given and how we can fetch it. Those are the two key points with which we are starting the notion with. And here they don't want to really go into those kind of things. They want to just go from scratch. You don't need to select a storage engine that is appropriate for application, as there are many out there and can be fine tuned. Although what is being mentioned here is that there's a big difference between the storage engines that are optimized for transactional loads and those optimized for the analytics. So the storage engines that are available, I believe, are meant for two primary purposes, or rather modeled around two primary purposes. One is the transactional workload and the analytics. It depends on that. They are kind of fine tuned in that area. Moving ahead, the fundamentals which this chapter starts with is that if you have to store and fetch something, the very fundamental part is a bash function where it's like a map where we set the value. The example, as you can see, is given over here. We say db set echo 1 comma 2 as database, and then a fetch command is written as db get, and accordingly the latest value is returned back. These are the very basic structure this area talks about. And an example given over here, as you can see, is it takes the key as 1 2 3 4 5 6, and it sets this entire JSON structure to be its value. And I'm sure the nesting is self-explanatory, where attractions is an array, and then there is a key value pair name and London, and that structure is represented by 1 2 3 4 5 6. Similarly, 42 is being set against a JSON structure with a similar format of name as San Francisco, and the attractions as Golden Gate Brigade, and the fetch is db underscore get 42, which brings back this value. So the starting of this book basically talks about these basic structures, and further, if we have to basically just see the entire thing, there's a cat command over here which runs and fetches everything all together. So that's the starting point, where we are looking at the very basics of setting and getting things back. Now we start to build upon that theory, and the first approach that we take is, let's take a file and put some data in that. Let's start by appending a file, and we keep on appending the data. And this approach of appending the data on the file is called as a log, right? Um, so in this case, it also highlights that the DB set has a very good performance over here, because we are simply appending things. There should not be any challenge. On the other hand, the DB get basically faces a problem, because as the data will keep on piling up, the get part of the operation needs to scan the entire database file. And as per the notation of ONN, we are looking at O of n as the performance here, which definitely seems that we need to optimize this. So this is the first approach that we are starting with. We're taking a file, even appending the data one after the other. So that's the whole intention of this chapter over here, at least the first section, which we'll be exploring the different type of indexes. So in this chapter, we will be looking up at a range of indexing structures and see how they compare with each other, and the general behind them is to keep some additional metadata on the side, which acts like a signpost and it helps you to locate the data you want. If you want to search the same data in several different ways, you may need several different indexes on different parts of the data. So obviously, as the mention over here, that the DB get basically is suffering, and in order to improve it, we are going to use index. And depending on the kind of data, the purpose, our indexing keep on changing. The index basically, as mentioned here, is additional structure that is derived from the primary data. I'm sure everybody understands what an index is, and it affects the performance of the query. Maintaining additional structures incurs overhead, especially on write. So that is a cost we have to consider when indexing comes into picture. And as mentioned over here, that the index basically slows down certain writes. To what extent, I am not able to quantify, or I'm not aware to a level of quantification. But yes, it adds a little overhead on the writing part, because the index also needs to be updated every time the data is written. Okay. Yeah. So here we are going to talk about the first index. Till now, any questions anyone has, or anything that anybody wishes to add or ask about, if it's not clear?
So what kind of data, I mean, index will use what kind of
So this is the starting point. It basically tells that the DB get, right? Our problem statement was that the DB get is not that good, because we are writing things through DB set, and that's fantastic, right? It's fast enough. But the challenge here is the getting part, because if you have a very big file, fetching becomes a overhead. So in order to optimize that, we are introducing index, and this is just the starting part. It's just giving an idea of what an index basically is, and what is the intent behind making an index, and what are the pros and cons of an index.
so
Yeah.
index will be somewhat like hash map, right? Corresponding to this, you'll have a value so that in constant time you can fetch it, isn't it?
Uh,
Not
I
sure. Okay,
would not
let's go.
100% say yes to it, because I feel my personal experience, it depends on the nature of the index.
Okay.
Because I believe in this book, they talk of three different indexes, which is hash index, SS table, B trees, right? So depending on the nature of how it's built, and maybe it might explain if it's really a hash map thing or not.
Yeah, SS tables and all that is the hardest. Yeah, let's go.
Yeah,
We can.
cool, cool, cool. Okay, so we start off with the first approach, which is the hash index. Uh, the idea is that we basically use the help of key value stores. So the problem statement now we have come to is fetching or reading. No doubt, at the same time, we are trying to understand how our writes can be better, and or our writes don't get compromised with the help of the indexes that we are using. So first index, hash index, key value store, very similar to something called as the dictionary. Okay, and as a standard implementation, we are looking at as a hash map. Hash map we know very well is a key value structure. So the whole idea here is that whenever, so as you can see in the diagram over here, the example is that there's a file, okay, at the strip basically has the values one after the other, but the intent over here is to mark the offset over here of the data being added, the key being added, and put it in a hash map. So the examples mentioned here is on the zero index byte offset, the value 1, 2, 3, 4, 5, 6 is getting added. Similarly, for the 64th index, you can see 60, 1, 2, 3, 4, the key 42 is getting added. So at a particular offset, it's like a pointer mechanism where the map will hold at which location a particular key is there. Um, okay, so just for participation purposes, I'll just ask someone from the audience if I had to add uh, let's say London, right? As a not London, no. Let me switch. Okay, there's no other example over here to talk about, because there's a slash and ending over here, and 1, 2, 3, 4, 5, 6. The entire thing goes till here, and then 42 starts from here. San Francisco attractions, Golden Gate, and ends here. Okay, cool. So fine. I mean, I hope everybody understands this part. So that is the intention of this first index, which is the hash index, where we are basically getting a map, and we are storing the offset and the key. Now let's elaborate more on that idea. So it obviously sounds very simplistic, and in fact, this is essentially what there's a product actually mentioned over here, Bitcast. the default storage in React. I did not really know about these two things before. So Bitcast offers high performance reads and writes subject to the requirement that all the keys fit in the available RAM, since the hash map is completely kept in memory. And also another point being mentioned here is that if that part of the data is already in the file system cache, a read doesn't require any disk IO at all. So there's a caching system also for this particular engine, which is called as a Bitcast. And obviously it gets updated frequently. So this is a bit of an understanding of what Bitcast is. Now we take an example. The example here is that the intention is to store the URL of the cat videos, and we need to store it the number of time it is played. That is the intention, and yeah, that's the intention. And so how to deal with this now? Okay, uh, so we are looking at an example where we are storing the video. Let's say the reference of the video is meow per and so forth, and we are adding it the number of times it is adding. But the approach taken over here is it will keep on adding the value, right? It's not going to go and check that was meow written before or was per written before or not. It's just going to keep on appending it, right? But in this case, what will happen is we're just piling it up, and the problem that we might head in is the disk space, right? We might run out of disk space. So how to deal with this problem? A very traditional approach given here is that we break that into segments, right? Rather than we keeping the entire thing and we working on it end to end, we break them into segments. A segmentation would work on the concept of a size. Whenever a certain size is reached, the segmentation will happen, and they will break up into segments. So that is the first part that we are looking at, is how we are avoiding the disk space issue. Furthermore, the other part of this utility here is that we are using compaction. What is compaction basically is, now since we are adding these entries one after the other, uh, we want to kind of let go of the older values and also try to get these segments together, merge them together, right? That is the whole intention of the compaction. So compaction means throwing away duplicate keys in the log and keeping only the most recent updated key. So if I look at this example, there are two segments that got created. Meow and per kept on getting appended in these two segments. The intention is that eventually the compaction should happen, and we should get the latest values of these three things, namely yawn. So if you look at yawn, there is one entry over here which is 511, which is we have put over here. There is meow. Meow has multiple entries over here, 1078, 1079, 81, and finally 82. So we'll take that 82 over here. Then the per has 2108. So it has multiple entries again, 2103, 2104, then 05, 06, 07, and finally 08. So that is the intention, that, okay, we got a file. The file was broken into segments. So to avoid disk space issues, and once that happens, we want to get the latest value, right, by compaction. um, that is the example here. So far I hope things are clear. Any questions so far? uh, Anybody has not understood anything, or wishes to add something more to the elaboration?
So what's the difference between compaction and file merging?
Fine merging,
I mean, there are
I'm
two
not
terms, right? One is compaction and then the
fine
merging.
merging. Okay.
Yeah.
Okay,
So I
you're
think
saying,
I think you
yeah.
highlighted, right? Yeah, yeah.
Yes,
Merging,
yes, the
compaction.
merging and the compaction. Okay, so the compaction obviously is talking about throwing away the duplicate and keeping the most recent one. So I believe that is the compaction. And
So,
merging, yeah.
so in
Okay, go
compaction,
ahead.
even the null values will be removed, or only the duplicates. Like, let's say some key is there, but there is no value corresponding to that. So those things should also be removed, right? Or only the duplicates should be removed.
So I'm not sure about if they were considering the use case of having null or empty values.
Okay.
But having said that, if we do consider, yes, uh, we might
Because
want to have that processed during
yeah,
compaction.
because
So what do you mean by null and empty values? I didn't get
null,
the
like
question.
corresponding to key, you don't have any value. So unnecessary, it's occupying space, right? You can remove it, right?
I think that will not happen, right? So when you update something, you will update with some value.
But in case you want to delete some value.
Oh, for the deletion will be
Then add none.
they mark as a tombstone. So the cleanup at the time of file merge. When you want to delete the
Right.
they mark as
In
a
case of
tombstone.
compaction, yes. Yeah. In
I
case
think
of
so.
compaction, that key can be removed, and later in in merging, we can concatenate multiple segments together.
Yeah. So I think it's more to do with the engine, the rule engine or the storage engine has to take a decision here how it is created. Although I don't see they have considered the use case of having null values or empty values, but then I feel it would come down to the storage engine. What does how it has been designed? Has it been designed to completely let it go? Has it been designed to add it over there, considering it as an empty value? I mean, it could be either the case, right?
Maybe depend on who's.
Yeah. Can you also discuss disadvantages of such index? It's hash-based index, yeah. Can we discuss the disadvantages?
Yeah. The disadvantages are discussed further along with the advantages.
Oh, okay.
Uh,
Thank you. Sorry.
Yeah. They have done that. They have spoken about how this approach is going to help, and also why there could be some problems with this approach. We'll be discussing that.
I'm a bit confused about one thing. Like previous in this example, that there was a key and then they stored an entire object.
Okay. Yeah.
Can you go up? Yeah, I
Yeah.
don't get why we are doing this with the index. We are creating an auxiliary data structure. Why are we dabbing around with the original data?
Okay. Cool. Right. So basically, we know the problem statement, right? We wanted a data structure to store things. We came up with a DB set. Then we evolved to a file. We want to append the file. So when we say a file, we are looking at a continuous stream of data we keep on adding to that file. Maybe CSV, maybe a JSON file. It could be various extension we can think of. But the idea is that we keep on adding things. And then the question came that if you're adding things, right, adding is very easy. We just keep on dumping the data. What about fetch? Fetch was a little compromised area, because let's say if this entire structure is available, right now we have two things over here. There's 1 2 3 4 5 6 as one key, and then there is a value named London attractions Big Ben London Eye, and there's another key 42 named San Francisco attractions Golden Gate Bridge, right? There are two entries here. So now if you have to fetch something, I have to actually go over it till the very end, right? Searching is very problematic. O of n, I believe, is what was mentioned here. See, I have to scan the entire database file, which is the cost is O of n. So in order to address that, what we did was we came up with the approach of maps. What the maps will do is it will hold the offset of the key. So rather than searching the entire strip over here, it would look inside the hash structure over here, data structure in memory hash map, as said over here, and try to look it up that, hey, do I have 42? So rather than searching one by one, character by character, I might, just look at this hash map table. Is it clear till here?
Yeah, sort of. Yeah, makes sense. But
is
then,
still... Yeah. Go ahead. Ask the question.
I would say if instead, if I want that object, I would store like a memory reference there. That would be more easy, and then get the actual data from.
Yeah. I think they were trying to do that only. That if you look at the offset is as good as if you in theory, if you think about it, it's like a memory reference. But
okay.
Yeah.
So I guess when we append in the file, we go by like byte offset by offset in the programming too. I remember.
Yep. Yeah. Character by character.
Yeah.
Yes. Index by index.
So that's why they have represented like this way.
Okay.
So coming to the next part of your question, right? Why index? So obviously we were in this place where the map was there, fetch was happening. I think so. We were doing good, but we wanted to optimize it. And yeah, I mean, yeah, that's the whole idea, right? That's why we came to the hash map thing. That this will serve as an indexing mechanism.
Yeah, I get it now. Yeah, sorry. I was bit
It's okay,
diverted.
guys.
Yeah.
Nothing needs to be apologized for. I mean, initially when I read it first time, I was also in pieces and it's all over the place.
So nothing prevents us
Okay.
from having
Yeah.
another key, right? We can have another index too, right? Pointing to the same data. Nothing prevents, this architecture doesn't prevent that, right? I'm just thinking, I don't think there is anything like, we can always have another index pointing to this data.
Right, absolutely. Because that was what was mentioned here, that depending on the search, depending on what we are looking at, that particular index would be structured according to it, right?
Okay.
The idea behind them is to keep some additional metadata on the site, which acts like a signpost and helps you to locate the data you want. If you want to search the same data in several ways, you may need several different indexes on different parts of the data. So as rightly said, it's like a metadata, it's like a signpost. Now, how we structure it depends on our purpose of fetch that we wish to achieve here.
The key,
And accordingly,
the key in the hash map, that's not the index. I thought it's kind of index, no?
It's kind of an index. Yeah, it's more like a structure they are creating for indexing. This is like the metadata. This is like the signpost. If somebody wants to search for a particular key value pair, they will look at the key searching in this table rather than searching it manually in a sequential manner over here, one after the other. They would first look it up in this structure, in this in-memory hash map.
So I think I forgot the basics of indexing. Indexing is for lookup of specific key or value, or indexing is more for like querying for a sorted kind of thing.
I mean, in general, from even what I remember, in general, indexing basically created that sorted structure for us. If I remember, MySQL uses this B-tree structure where fetching becomes faster if you have the indexing done. That's a very, very general thing I remember. If anybody feels otherwise.
Yeah, even I think the same thing. So this key byte offset map, I don't think we can call it as an index, maybe.
Okay, let's see. I mean, they start with this hash indexes.
Yeah, I don't want to. Yeah.
No, that's perfectly fine. It's perfectly fine because I also tried as much as I could. I'm not able to complete the entire chapter, just half of it. So definitely, discussion helps. Any sort of discussion would help for sure. Okay. Cool.
Is there any other database which uses such kind of indexing? Like in this book, the example has been given of React, right? So is there any other database in here which you know or anyone knows?
Not much. I am to learn it now, obviously, through this chapter. But if someone else share something. Okay. So, I mean, best to my knowledge, I remember B-tree is the one. And then there is hash indexing also in MySQL. So maybe we can quickly look it up after the session of how indexing is created. I think I remember in MySQL, by default, it's a B-tree. But if you want to change that, there is a mechanism. But internally, what it does, I also am not aware. But yeah, if there is something available on the internet, we can definitely explore that more to understand that. But yeah, right now, what we're talking is definitely a very, very tip of the iceberg kind of a problem area where we're just starting off something simple. And then maybe after that, it grows up to sorted tables, then B trees eventually.
What is that you're saying? So internally, how it is doing? What is the question here?
I think Nitish had a question regarding different indexes available. So I just remember on the top of my head B tree.
Yes, yeah, actually, I just wanted to know if this such indexing is used by any other database engine. Like in this book, the example has been given of React. So I'm not aware of React, and I don't know if any other database engine uses such type of indexing. So I just thought of asking.
So generally we have.
I think.
Go ahead.
Yes, Sridhar, go ahead.
Yeah, generally, so we have two kinds of indexes. Mostly use that. One is B tree indexing, other one is the LSM trees. So B trees are used for the SQL kind of databases, and then LSM trees majorly famous for like NoSQL. I think if you go further down, they will explain about that. Yeah.
So LSM is that comparing the hashes, right? At the
No. That hash case is the basic one that will not use anywhere.
Okay.
Whereas LSM tree is like we create SS table and then SS table will be maintained. Yeah, it's similar to that. Yeah, hashing, they maintain SS table hashing. Right.
We compare the hashes of two, whether two documents are same, and then they go to the parent node. Subsequently, they reach to it. Yeah.
Yes.
Yeah.
Cool. Okay, so resuming back, compaction and merging was going out and doing stuff. So merging and compaction of the frozen segments can be done in the background thread while it is going on. We can still continue to serve and write the requests as normal using the old segment files. After the merging process is complete, we switch the read request to using the new merged segments instead of the old segments, and then the old segment files can simply be deleted. I hope this paragraph is very clear to everyone, where there's a background job going of merging and compaction, and the moment that part is done, then the pointer of read is switching to the compacted segment, and it reads from there, and the old segment is moved out.
So I'm just wondering, like, suppose I want my previous value to, so it's compaction is like it's updating the value, right? But I want for my log purposes, I want like what was the previous value. This is not going to solve it, right?
Yes, it will not solve this purpose of maintaining a log or a history of what was there before and versus what we have now. At least in this particular use case.
We can take the snapshot at every level, right? Or every after every transaction, something like that. That will help.
Correct. There are approaches that, I mean, if we go a little lower in the chapter, it talks about approaches of how that can be taken care of. One is snapshots, one is capturing offset, the last red offset and the value. Some approaches are there. But yeah, that is there.
So here I think they maintain only one version of the value. They don't maintain multiple versions.
Correct.
So
in this use case, it's all about the latest. Yeah. In this use case, they intend to get the latest value of that particular key. So yawn 511, meow is 1082. Even though we have 817978, right? But it takes the latest one. And per, as you can see, 2108, not 21075 and so forth.
So sorry, I forgot what was the use case. Actually,
use case. Yeah, they wanted to first of all create segments, but at the same time, this was kind of reading and adding. So adding out data was happening, reading from the map was also happening. But now we're trying to optimize, right? Eventually, my segments are going to fill up the memory; they will kill it. So we have to remove the segments or reduce them. And one way of doing it is just going through the segments and reading the latest value and getting rid of that particular segment. So that is one of the approaches in this use case.
So we are designing what? We are trying to do what?
We are not designing anything. We're trying to understand a concept through a use case of index. The first index that we saw here is the hash index, where a map is getting created and that stores a reference of the value in a file, right? That is the problem statement, and we are building certain knowledge on top of that, step by step. It's I would not say we are addressing any bigger problem here. We are just trying to evolve our simplistic data structure of set get to a file where data is added or data and data is read to further taking to the next step is optimizing or making the file smaller in this case. That
Okay.
is where the stage that's the stage where we are right now. Okay, cool. So as per this paragraph, the thread will go, this processing will happen, and once that is done, this will become the new segment that it will refer to. Cool. So with this approach, what happens is, each segment has its own in-memory hash table, right? And whenever the search has to happen, so let's say the compaction is not done. So what it will do is it will keep on reading segment by segment. It will try to search, okay, let's take a use case, mu or yawn. Okay, they all three are here. Okay, let's say that it started searching for yawn over here. So it searches here in the segment 2, it's not there. Then it will go to segment 1. It will search for yawn and it finds it. So it will go segment by segment, as mentioned over here. It first checks the most recent segment hash map. If the key is not present, then it goes to the second most recent segment. So it will keep on searching that way, segment by segment. That is the approach of searching.
So here corresponding to one key, you will have multiples, list of values, list of segment offset, right?
I believe
Like,
every
let's say there are,
segment will have a set of maps of it. So this segment will have its own map. This segment will have its own map. That's what my understanding is here.
That's true, but how will you go to that particular segment, right? Let's say there are 10,000 segments, right? And you have to search anything. First, you need to go to the local area, right? Where that, in which particular segment it lies. And from there, you will go inside to find where that particular key is present in that segment.
You're referring to some kind of an orchestration mechanism which says that this is the recent segment, this is the next recent segment, that kind of a technique.
I think so. What is asking is like if you have multiple segments, how would we search for a key? So what we do is first there's a very recent segment, right? So that we maintain in memory also the cache. First we check it there. If the value is present there, we give that value. If it is not present, then the timestamp of creation of the segment, right? We go the incremental order, not incremental, decremental. So that for order we follow the timestamp order, which is the most recent segment. In that we'll check the values present. If it's not present, then we'll go back to the other segment. Like that, we go till the last segment.
So in worst case, it will scan all the data file segment, right?
Yes. Oh yeah, for that, there is a solution for that actually. They use the Bloom filter to avoid that.
But Bloom filter is again probabilistic, right? If something is present, it may say, it can give you only if it is not present, then it will give you the correct answer, right? So
yes, so we need that, right? So the value is not present means it says it's not present. So that is enough, right? To search the whole segment. No, if it is present, then we don't care, right? No, if it is present, then anyway we need to scan all.
Yeah.
So the value is not present, then in that case only we check all the segments, right?
Correct.
Yeah, that scenario we can avoid by using Bloom filters. Yeah.
Makes sense.
So in the cache, what kind of data will be there? Like now I understand, like for each segment, they have in memory hash table. So now we are talking about like how we are searching for the segments. So for that, the solution is like we will create one another map that we are saying as a cache, right? And in that map, what is the key and value?
I think what I said, that was similar to SS tables. That's why, like, right, first you go to the particular segment via the hash table. Next hash table will give you the offset in that particular segment where that particular key is present, right? But Bloom filter is the solution as of now.
Yep. The Bloom filter really is a very valid point here.
Correct.
Yeah, I mean, detailed description right now, we don't have it, at least in this chapter, as to how
Yeah,
these
yeah.
entire segments are being tracked in terms of sequencing. But yeah, the approach at least they have given here, that how the searching will go by. It will go segment by segment, hash map, obviously, the segment by segment hash map, and keep searching till it finds it. That's the intention.
So worst case will be you scan everything from recent
Correct.
most.
Oh, fair. Yep. It will scan everything, worst case. That's correct. Cool.
Here I cannot, like here it's showing merge segments 1 and 2, and it's showing only the duplicates one. It's not, it doesn't have all the values for the segment 1 and segment 2.
I think most updated value they are showing, right? Let's say
Correct.
yawn is present in your one file segment, so it's showing. Now when you come to scratch, for scratch, out of these two, most recent they'll pick, right?
Correct.
250, because that is how we say. I think. Yeah, go ahead, please.
Yep.
But
So it's
scratch is
basically
not here
logging.
in the data segment file 1.
Yeah, because
but
it
that
will not get appended. The appending is random. It's not that it has to have one of the values. It is just appending it one after the other. It just takes the value. So it found that, okay, mu is now played 1078 times. It recorded that. Then it got a new update that per is playing 2103 times. It updated that. Then it got another update. I'm just giving a hypothetical kind of thing. And per is played for 1024. Then it added that key value pair over here. I mean, at least that's the approach taken over here so far.
Yeah, that is because the per is having 2114, right? That is the most recent data. So that
Most
is what
recent.
after merging they are substituting
Correct.
this value. In mu, you can see
Got
mu
it.
also having 1087, which is most recent in your second segment. So that is what they are jotting into, right?
Yeah, got it. Yeah. No, I thought like there are more keys, but after seeing, I've been carefully looking into it. It's like only we have 4 keys.
And yeah, in this use case, it's only 4 keys.
Yes.
Cool. So basically, it gave us a lot of theory and pointers, and now it tells us that, okay, if you have to actually do this real time, okay, what are the implications? First and foremost, it's the file, the format of the file. One point it says that CSV is not going to be the best approach for this. It has to be some kind of a binary format, right, where it takes bytes, in terms of offset by offset. So that's the first thing. Second thing is the deletion. So now, during the process of compaction and merging, we are definitely looking at the stale data, the stale segments. So those data, so that approach of the deletion of the record to the data file is called as a tombstone, where the logs are merged. The tombstone tells the merging process to discard any previous values for the deleted key. Right, so that's the process of deleting, where tombstone as a concept has been introduced over here. Other approach, other implication is the crash recovery. Okay, let's say that there was a crash for some reason, right, and the in-memory hash maps are lost, right? Those are our references. So how do we get things back? How do we recover them back? One of the approaches mentioned here is that we note the last read offset. Okay, noting down the offset of the most recent value. That is one approach. But although even doing that might take a long time if the segment files are very large, because we still have to search again for that offset. Example it gives here for Bitcast here is that it speeds up recovery by storing a snapshot. Yeah, a snapshot of each segment hash map on the disk where it can be loaded. So that is one of the way of how the recovery can be taken care of. Either we store the offsets and do things, or we store the snapshots as per the that Bitcask thing.
Bitcask is what, another name for a snapshot or what?
No. I think it's a different tool or a database. I don't know what exactly is. It's something. I'm not gone that much deep. It's a part of React though. That's what it mentions in the first. Maybe we can Google it, so we'll get some. Okay, then the other implication is the partially written records. So data was being read, and during the writing, it broke, right? So how do we take care of that? Maybe so these are all trade-off discussions kind of points over here, right? So a point mentioned over here is that maybe including checksums. Checksums can be allowing such corrupted parts of the log to be detected and ignored, and there would be a mechanism to start over again, writing on the certain area. Uh, concurrency control, right? Now, so here it's the part which I have not understood what is it's trying to say. It says that as writes are appended to the log file in a strictly sequential order, a common implementation choice is to have one writer thread. Data file segments are append only and otherwise immutable so that they can be read concurrently by multiple threads. So I didn't really get this part, what it was trying to say. When it says sequential order, uh, uh, I mean, I understand it's adding one after the other, and that's the writer thread, I suppose. And
Yeah, so what I after reading this, what to me, like there will be one writer and multiple reader. Why is that? Because we are just append only. So if you have appended initially you have written one data, it is not going to be changed. So nobody can write there. So there will not be any writer thread again doing the first whatever you have written. So multiple reads is the safe, like concurrently anybody can read it, and there will be one writer which will write sequentially.
so here's the thing, right? I understand that that destination file is a single file, right? But I couldn't quite understand why do I need one writer thread for it? Maybe I can have multiple writer threads and just keep on
But
adding, because I have to just add things one after the other,
se-
right?
so sequentially, how will you add if multiple threads are there? It has to wait, right, one at a time and then followed.
Yeah, that's where my confusion was, that why is it talking about a sequential order when we know that we have to go and fetch the latest one? Unless there's a logic built in the search engine or that storage engine that always search from one side because it's in a sequential order, then it could be the case. Uh,
Mhm.
No,
yeah,
write is always the sequential, right? This is what we are reading. Write in a file is always in a sequential order. Like we are just appending it. We are not deleting anything from there. After the processing, whatever we are doing, that's a different scenario. But initially, we are writing always. We are just appending it.
right. No, my thought process was that we can have multiple threads writing it one after the other. Because so I'll give a use case where I was coming from. The use case is that, okay, one file is reading the details of per, one thread is writing the details of per, one thread is writing the details of meow, one thread is writing the details of yawn, because it's just adding it one after the other, right? So I was just wondering that why should I limit the writing to a single thread? I could have multiple writer threads where per could be written by one thread, and it keep on adding for per, mew for the thread for the mew, it could just keep on adding for meow, right? And yawn, it could just keep writing for yawn, and it would still achieve the idea of sequential ordering, right? uh, I mean, that's what my brain was going in that direction.
Yeah, that's a yeah, valid point.
So uh, yeah, that was my thought, I mean, which I had a little bit of question. Yeah, I mean, obviously, anyone else feels otherwise, please contribute. I can see there are lots and lots of people uh, in the list.
So rather than taking the updated value, why didn't they maintain a list corresponding to one key where multiple values could be there, old value to the most recent?
Yeah, then you have
Uh,
to do that timestamp thing too, right? I mean,
Uh,
in the link list as well.
mhm.
Yeah,
No,
yeah,
like list of values corresponding to one key. So that's you were telling regarding log, right? So everything will be there. Here you are updating, so you won't get the previous value. I mean, you have to take the snapshot and all those what was mentioned, right? But again, I think search time will be off and right corresponding to one key. Here also it will be same only.
mm,
Yeah.
What I think is regarding the one writer thread, I'm not sure if I'm correct, but I remember that even if we use multiple threads to write to a same file, ultimately OS is going to do that sequentially. OS will never allow multiple threads have their own view of the file. So OS will make sure that only one of it will be sequential. So even though we are using multiple threads, ultimately they'll get blocked at a OS level and they will be sequential. So there won't be much performance gain with multiple writes. So that's
No,
what I think. Yeah, right. Though we might use multiple threads, OS is going to execute that write in a sequential manner.
Do you mean like it will take a lock? There will be a lock at OS level when they are writing.
I think so.
Writing.
Yeah. Yeah, should be some sort of lock mechanism must be there. Yeah.
But, okay, I think I'm not sure. Like
I remember reading this concept in OS.
Yeah, but when two threads are writing at the same time, we cannot guarantee like they are not. Let's say a record of 100 bytes is writing, and another thread came in, and it first thread is at 20th byte. Then second thread can come and write at 21st byte. So this kind of thing can happen without lock. So I think it's the application's duty to have a lock and then execute. So that's why I
So in any application, when you try to write to a file, you will first take a. Yeah, so I think we will first need to like say if it's Python, you will first take a open, right? Like you will try to open that file or in a whatever language it is. So that step itself will sort of I mean internally OS will basically take lock and allow that particular process to do the writes. Yeah.
Okay. Python might have something like GIL.
Any language, even C,
that,
even C.
Yeah, in that case, we have to take a look explicitly. Means this is as per my experience.
Yeah, so without opening the file in any application, we can't write to it, right? So that open step itself will it's nothing but a lock, I guess.
There will be no. I think there could be two pointers where you can open a file in an append mode, right?
Mm-hmm.
That we can do. So then using both of those pointers, it's possible to read at the same time.
Okay, not sure. I mean, I don't know how append mode works. Like if OS has something like an append mode sort of thing.
Okay. So yeah, I guess I mean yeah, as Amit has mentioned, one one thread to write is more from an integrity of data purposes. I went in a direction of data specific. So maybe in realistic terms, maybe it's not limited to 4 data entries. It might be like lots of entries. So creating a separate thread for all of them might be a challenge, or might be getting into some problem statement area. So maybe that's the reason why single thread for writing is preferred here in this case. But yep, good discussion in terms of a good point with regards to OS, kind of maintaining that kind of lock of writing for that file. Cool. Okay, so yeah, anybody has anything else? Okay, moving further. So these were the certain implications. Then the author basically throws another point over here, like why are we going approach? Why don't we update the file in the place, overwriting the old value with the new value, right? why are you just going on adding it? Might as well just update the old one, right? So I hope this change in approach is clear to everyone here, where it says that append, override, my bad, not append, override the older value with the new value, right? So what are the benefits? Obviously, appending and segment merging are going to be faster than the random writes. Uh, in this case, more details coming up later on, so I'm not going there for now. Then concurrency and crash recovery are going to be simpler if segment files are append only or immutable. For example, you don't need to worry about the case where a crash happens where a value is overwritten, leaving you with a file containing the part of old. So you don't need to worry about whether it's an old one or new one. You know that this is the value. Now it's up to us. We want to update it or not. And fragmentation is what is referred to as another benefit, right? But then with this approach, there are certain limitations. Now, what are the limitations here? Limitations are that at the end of the day, this entire thing takes up space. Right? It has to fit in the memory. In principle, we might have to put all of this map on a disk, which is sometimes challenging in terms of the random IO access. Now, I'm not sure how this thing, but I'm just going to go by the statement here that it requires a lot of random IO and it is expensive to grow when it becomes full, and hash collisions require fiddly logic. So I probably need to check that stuff out, what it is. But this is one of the limitations as mentioned here. And then obviously the next point in terms of limitation is that range queries are not efficient. For example, you cannot easily scan over all the keys between kitty 000 to kitty 9999. You have to look up each key individually in all the hash maps. I get the part where it says that we have to look up to the keys individually in the hash map, but not sure what it means when it says range queries are not efficient. Because right now, from what I understood, they're just storing the key and the offset in the map.
But
I'm not sure.
if entire map can't fit in your memory, you can't do a range query on it, right? Like part of them will keep on the hard disk, and then rest of them will keep in the RAM.
So
Okay,
even if it's fit in the RAM, right? So we cannot do this.
So is it more to do with the partial storage on RAM and memory? That's
no. The thing is in RAM, right? So while storing it, so the keys will not go in a sequence, right? So the hash mapping, the keys will not be in a sequential order. The storage. So in that way, when you're trying
it is being stored also sequentially, right? If you look at the map, I think they just store it on the basis of the offset found. Right? It just says that, okay, this is the key, this is the offset. This is the key, this is the offset.
Right. So
right?
we don't maintain a sorted order.
Yeah, there's no sorting here. Exactly. No sorting. So in this case, what is exactly the range based?
Oh, okay. So when you say range, right? So something like this. Say for suppose you're trying to query number of people between the age 18 to 20. So that kind of range, right? So if you maintain the range, the storage in the order, then only you can query the age between 18 to 20, right? Something like that.
So basically, it's not happening. Yeah. So basically, it's no, but it's the wording doesn't say that it is not possible here. It is saying that are not efficient.
Not efficient. Not efficient. Okay. Everything is possible. You can go. You can search the whole hash table and then make it.
Got it. Yeah, now I get it. So we can do it. It's not impossible, but it's not efficient because it's not ordered. That is the problem statement here. Okay. Okay. So I hope everybody is clear with the problem statement which is mentioned here and the benefits of the alternative of what is happens if we go for the alternative.
Yeah, I think this looks good. So fragmentation is like can't fit into the memory, right? Merging whole segments avoids problem of data files getting fragmented over time. Fragmentation is that what we study in numbers, right? If the process can't fit in one like slot, then you chunk that process and then
I think it's more about chunkify how the segments are getting created. That's what my understanding is in terms of fragmentation. Anybody else having thoughts on this?
Yeah.
Okay.
no,
Okay. Yeah. So that's where this hash index ends, and the next table starts. So I have just partially gone through this. I've not completely looked into it, and
Yeah,
I
so
think
we
so.
can
Starting this fresh would be a good idea, so that we have that continuity rather than doing half and then resuming half later on. So yes, guys, that's how we are doing it, and hope hash index at least people have. I have everybody has an understanding of what was being done in terms of hash index.
So where, so in SQL it is used, right? I think Nick mentioned hash index, right?
Sorry, come again.
I mean, where these hash index are in which all DBs it is used?
I think that database Bitcast React is what it gave the example for.
Nick has said one. MySQL.
Yeah.
Yeah, I think then we can wrap it up.